Hey everyone, welcome to your video lesson for today. We are still in chapter 4. There's really 5 sections that we go through in this chapter, but there's a lot of content in there. So today we're going to be focusing on MVT, which you can see below here means mean value theorem. We're going to talk about average value and do some application problems. I'm also assigning you all another video for the second fundamental theorem of calculus. I just thought that video would maybe explain it better than, it would just give you guys some variety, okay? So let's start by talking about the mean value theorem for integral. So the mean value theorem, it basically states that somewhere between the inscribed and circumscribed rectangles, so remember inscribed, remember those are the ones that are kind of underneath your curve. So for instance, a rectangle like that would be an inscribed rectangle. A rectangle like this would be a circumscribed. It's outside of your curve, right? So inscribed and circumscribed, somewhere between those two, there must be a rectangle whose area is exactly equal to the area of the region. So we are saying that the area of this blue shaded rectangle right there, that area must be exactly equal to the area of the whole region under this curve. What we often want to do with these problems is try to figure out, well, okay, what C value would give us the perfect height, f of C, to find this area of this rectangle. All right, so for this, I can say that the area of the inscribed rectangles is going to be less than the area under the curve is less than the area of the circumscribed. Like, we know that, we've been doing that. And what we're saying here is that I will have a rectangle, and the way I calculate the width of that rectangle would be height times base, or width times length, however you want to say that. We're saying that the area of this rectangle exactly equals the area under the curve. So here is your exact mean value. You kind of saw it on that previous page over there, but here it is again. This right here, of course, represents the area under the curve perfectly, right? Exactly. This over here represents the area of that special rectangle. And we're saying that these two areas are exactly equal to each other. All right. Again, I have some conditions. My function needs to be continuous. We're on this closed interval from A to B. There's going to be some number C. That's often what we're trying to find in these types of problems. Mean value tends to get very combined with average value, and you'll see exactly why in a second. So the average value of a function, also always feel free to pause, take your notes as long as you need to in this section. I go a little quicker in the videos because I know that you guys can pause. So the value f of C in that mean value theorem, it's called the average value of f on the interval. So your average value is going to represent the height of the rectangle that has exactly the same area as the area under your curve, okay? This right here, this is our definition for the average area, 1 over b minus a. So again, in our closed interval, I'm going from a to b, so I'm going to substitute in b and a for these values down here. 1 over b minus a, write this equation down, times the integral from a to b of f of x dx. This will represent your average value. So this represents your f of c value. All right, let's try to understand a little bit more like why this is the case. So I'm going to kind of take you through a little bit of a proof here. So, what's going on here? So to see why the average value is defined in this way, I can partition that interval, we've been doing this, into n subintervals of equal width. Guys, you've used this equation so many times now, right? So that's representing width here. B minus a over n. If ci, again, you've seen that, that's any point in the ith subinterval. Usually we would use our right endpoint because that's just easier. But ci could represent any point in the ith subinterval. The arithmetic average, or the mean of those function values, would be 1 over n times, you're going to add up all those different f of c values, and you're going to divide them by the number value. So, and this is just representing an arithmetic mean. That's what a sub n would equal. Okay, so what the heck? And if I'm multiplying and dividing b minus a, so again, I'm going to scroll back up here. We have this expression over here, delta x equals subintervals b minus a over n. Now I'm saying, hey, I'm going to call my average the sum of all of these function values at all of these different c's in all of my different subintervals. I'm going to multiply and divide b minus a. I can rewrite the average like this, okay? I'm just summing all of those f of c values. The average, I needed to multiply by 1 over n, right? That is an arithmetic average. Add them all up, divide them by the number of whatever you have. Here I'm multiplying by b minus a over b minus a. I'm allowed to multiply anything by 1, right? Now I'm going to do a little bit of rearranging. I'm going to move this b minus a to the front, and I'm going to move this n to the back here. Okay, I'm just rearranging the order. We end up getting something that looks like this. And lastly, we know that b minus a over n, that's just representing your width, okay? So this is kind of the proof of how our average value is equal to 1 over b minus a, the summation of f of ci delta x. So, yes, of course. So finally, if I were to take the limit as n approaches infinity, it's going to produce the average value of f. So I would need to take the limit of that, and we of course know the limit of a summation is equal to the definite integral of that function. So that's just producing your average value, your f of c, all right? So again, feel free to go back and kind of work your way through that mentally again. You won't have to do the proof for this, but I wanted to give you some background instead of just saying, hey, here's a thing, trust me on it, okay? So let's finally do an example. Find the average value of f of x equals 3x squared minus 2x on this interval. So here's our interval from a to b. They're giving us our function. We know that our average value, our f of c, you could say, is 1 over b minus a, and then the definite integral from a to b of f of x dx. Let's go ahead and plug things in. I'm going to plug in b and a, so 4 minus 1, and then I know I'm evaluating this from a to b, from 1 to 4. My function here is 3x squared minus 2x. I'm integrating that with respect to x. And here you can already see the answer is showing up for you. We're just going to prove it in our work. Make sure we get the same thing. Let's simplify a little bit. This first part just turns into 1/3. And then over here, I need to actually integrate. So 3x squared, the integral of that, I would add 1 to that exponent. I would divide the whole thing by 3. That's just going to turn into x cubed. And then minus 2x, again, I would add 2 to that little 1, that's hidden 1 in the exponent. I divide it all by 2. That would just be x squared. I need to evaluate this at both 4 and 1. That 1/3 is still just going to stay out front. I'm going to plug this in. 4 cubed, actually I'm going to go ahead and write out what 4 cubed actually is. So 4 cubed is going to be 64 minus 4 squared is 16. Subtract all that by 1 cube, 1 minus 1 squared, 1. Okay, we can simplify. 1/3 times 64 minus 16 would be 48. The 1 minus 1, those two are canceling each other out over there. And our final result is 16, which is the answer they said over here. So that average value, that f of c, that average value is 16. A rectangle with that height 16 and the same width from 1 to 4 is going to have the same area as that red shaded area under the curve. Okay, so that's combining kind of mean value theorem with your average value. Sometimes a problem will ask for average value. Sometimes it will ask for the C value. You will see some problems like that. I believe we are doing one later on in this. Okay, maybe we're not doing one later on. I think I had that planned. Anyway, sometimes they will ask you for the C value. Well, if I know that f of c equals 16, you could just set your function f of x equal to 16, so 3x squared minus 2x equal to 16, and you could solve this for x. You would basically be solving it for c then, right? So I know I should call this c. F of c equals 16, so I'm setting my function equal to 16. You could either write out the x's or you could replace them with c's if that's easier. 3c squared minus 2c equals 16, and you're solving for c, okay? But if you know your average value is f of c, then you can set that average value equal to your original function and solve for that c value, okay? So you will have some problems on a worksheet that's going to ask you for that. Use this tactic right here. Okay, there's another theorem that we're going to quickly discuss, our net change theorem. So this theorem says that the definite integral of the rate of change of any quantity f prime x gives the total change or net change in that quantity on that interval. Okay, so this looks, pretty familiar with what we've been seeing. I'm taking my integral over here, but this allows us to actually apply to do some application problems here. So easiest way to understand this is just jumping into an example, diving into it. All right, a chemical flows into a storage tank at a rate of, so here they're giving us a rate, 180 plus 3t liters per minute. And I know that t is going to be somewhere between 0 and 60. Find the amount of chemical that flows into the tank during just the first 20 minutes. So I'm going to do a couple things here. I'm going to let C of t be the amount of chemical in the tank, so C for chemical, the amount of chemical in the tank at time t. C prime of t, the derivative of that, represents the rate, which hopefully we can kind of connect that back with what we've talked about, right? Rate, derivative, we talked about position, velocity, acceleration. Velocity is basically the rate of change of position over time, right? So derivatives represent rate. So the derivative here represents the rate of flow at time t. All right, so here's how we're going to set this up. The amount that flows in 20 minutes, let me spell flows correctly. I'm going to set this up like this. I'm going to go from 0 to 20 minutes. So t is representing minutes, right, between 0 and 60. C prime of t dt. That is what this is saying up here, right? So I'm going from A to B. This f prime of x represents a rate. When I integrate that, it's going to tell me the exact amount that actually flowed during that time. So down here, this is equal to from 0 to 20. They gave us our rate. It's 180 plus 3t, and I'm going to integrate that with respect to t. The integral of 180 is just going to be 180t. The integral of 3t squared, I kind of give away the answer there, 3t squared divided by 2. And I would like to evaluate that at both 20 and 0. When we evaluate this at 20, we get 3,600, right? I'm plugging 20 in for t here and plugging 20 in for t over there. Plus over here, I would get, 3 times 400 divided by 2. So that's evaluating it at 20. If I plug in 0, I'm just going to get 0. So minus 0 for both of those. When we simplify this, I have 3,600 plus this would turn into 600 over here. Your final answer is 4,200. And again, this represents liters, the amount of chemical that flowed out in the first 20 minutes. So they gave us a rate. We integrated that rate to figure out the amount of chemical that actually flowed. So an application problem, will you guys be calculating chemical spills? I don't know. Honestly, maybe some of you might be someday. So this is an application of integration. They're giving you a rate and you are finding an amount. Another way that we can apply integration is thinking in terms of displacement. So this is another way that we're using our net change theorem. I can examine velocity of a particle moving on a straight line. S of t is our position function. Remember, we have dealt with S of t a couple of times now. The velocity is just the derivative of S of t. So this is just an alternate version of your net change theorem. When I integrate a velocity function, it's going to give me basically the change in position, or change in position is specifically called displacement. If you've taken physics, you've heard that term. If you haven't yet taken physics, you will hear that term a lot. Here's a way to graphically or visually kind of think through this. The displacement of a particle and the total distance traveled, they're very related, okay? But displacement, I would want to take into account when I dip below the x-axis. Direction or sign really does matter for displacement. So over here, if this was my velocity graph, to find my displacement, I would count this as a positive area. This would be counted as a negative area, so that's why I'm subtracting it right there, and this would be counted as a positive area. So displacement does take into account positives and negatives, because displacement is really thinking about, okay, am I moving forward, am I moving backwards? Total distance, however, would just be the absolute value of this. Total distance would just say, hey, take all of this area and just take the absolute value of it. So I'm going to be adding A1 plus A2 plus A3 to find my total distance. All right, so that is your difference here between displacement and distance. Displacement, take signs into account. Take signs into account. It does matter if you're dealing with a little area that's under the curve. For distance, absolute value. Okay, so you were just adding, it doesn't matter that this is a negative down here. You're just going to be adding A1 plus A2 plus A3. All right, so let's try an example with this. Here's our application. The velocity in feet per second of a particle moving along a line is represented by this function right here. And we have our lovely graph right over here. T is time in seconds. What is the displacement of the particle in the time interval between 1 and 5? So we're going to set up our definite integral from 1 to 5, t cubed minus 10t squared plus 29t minus 20 dt. So displacement, I can just simply integrate and evaluate at 5 and 1. Let's go ahead and do that. So when I integrate this, I'll get t to the 4th over 4 minus 10t to the 3rd over 3 plus 29t squared over 2 minus 20t. And I would like to evaluate that at both 5 and 1. If you need to use your calculators for some of these, you are welcome to. So 5 to the 4th over 4 minus 10 times 5 to the 3rd over 3 plus 29, 5 squared over 2 minus 20 times 5 minus, when I plug in 1 over here, 1 to the 4th is just going to be 1, so 1/4 minus 10 thirds plus 29 over 2 minus 20. So you can do this by hand if you want to, or you can plug this into your calculator. Either way that you do this, either way that you simplify this, we are going to end up getting 32 over 3. Because this is representing a displacement, it needs to have units. The units for displacement would be my distance units, so 32 feet. Because it's positive, we would say to the right. Right is positive, left is negative. All right, so to find your displacement, I'm going to scroll up. To find your displacement, you are simply integrating your velocity function and evaluating it at B and A. All right, and again, if you need help figuring out this part, you can plug this all into your calculator to make sure you're getting 32 over 3. You can do it by hand. It would get a little bit complicated there, but you definitely could do it. Make sure, though, for these problems that you know how to simplify to a fraction. I want to get an exact value. I don't want to get decimals as much as possible here. So that might mean, you know, simplifying this down to one fraction, simplifying this down to one fraction. So you can use your calculator as a tool, but use it to help you simplify. Don't just use it to find a displacement. All right, part B of this problem. Now they're asking for the total distance traveled. So when I'm dealing with distance, I want to think in terms of absolute value. So honestly, we didn't really use this diagram that much in part A, because when I'm finding displacement, I'm simply finding the integral. And as I'm finding that integral from 1 to 5, the process of integration is taking care of those positives and negatives for us, okay? But when I'm finding distance, I need to figure out what are my zeros of this function. So I have zeros at 1, 4, and then 5 over here. Another way to think about that is where are your x-intercepts? Where do you cross the x-axis? So I have zeros at t equals 1, 4, and 5. And we can see that v of t, that function, is greater than or equal to 0 from 1 to 4. But the function, the velocity function, is less than or equal to 0 from 4 to 5. So distance is actually a little more complicated than finding displacement from velocity, because now I need to split this into two separate integrals. Evaluating it from 1 to 4, I'm just evaluating the normal one, the positive version of this. T cubed minus 10t squared plus 29t minus 20 dt. And then I'm going to have to, you can think about this two ways. You could think, hey, I'm going to subtract the integral from 4 to 5, or you can think I'm adding the negative of all of this. I'm just going to go ahead and say, hey, subtract, because this part is under the curve. That would be like a negative area. You could kind of think of it. I did air quotes around negative there. So I'm going to subtract this whole one. And again, it's minus 10t squared plus 29t minus 20 dt. Both of these are going to have the same integral. You're just evaluating them at different values. So this would still t to the 4th over 4 minus 10t to the 3rd over 3 plus 29t squared over 2 minus 20t. I'm evaluating that at 4 and 1 minus, same exact thing, t to the 4th over 4 minus 10t to the 3rd over 3 plus 29t squared over 2 minus 20t. But for that one, I'm evaluating it at 4 and 5. All right, for all of these, I would recommend, try as much as possible to plug into your calculators for these. Again, you can do it all by hand. You could. But eventually we end up simplifying to get 8 over 3 minus negative 103 over 12 for this first section, minus 25 over 12 minus 8 over 3. Okay, when I plug in 4 and simplify, it should go to 8 over 3. We'll plug in 1, simplify, we'll get that. Plug in 5 and 4. It should simplify to all these fractions. When you combine those fractions up, it would simplify down to 71 over 6 feet. And that is our distance here. So again, the difference between distance and displacement is taking into account these positives and the negatives, but distance is just taking the absolute value. And it's just saying, hey, any space between the x-axis and the curve, whether it's above or below the x-axis, I'm going to count that. I'm going to add that all together. So hopefully we should see from that previous problem that we had, there should be a difference in your answers for displacement and your answer. Our answer for displacement right up top here was 32 over 3 feet. Distance was 71 over 6 feet. So there's a slight difference there. All right, good work with this video. Head on to the rest of your assignment.